Have you ever felt that little thrill when you get the notification that your online order has shipped? That anticipation as you track its journey, knowing it's on its way to your doorstep?
Oh, yeah, definitely. It's almost like a little gift notification.
Exactly. It's such a simple everyday convenience that, well, we often just take for granted. But what if I told you that behind that single notification, that simple act of a package moving from point A to point B, lies this immense, breathtakingly complex symphony of technology, logistics, and data?
It's absolutely true,
Yeah.
especially when you're talking about a market as vast and, well, diverse as India.
Right.
What seems like a really straightforward action for the end user, for you, is actually the result of millions of interconnected operations, all working in, hopefully, perfect synchronicity.
Millions. Wow.
Yeah, and building a system that can handle that kind of scale and complexity from scratch reliably day in and day out.
Hmm.
That's a monumental engineering challenge.
Yeah.
Absolutely. And
Okay.
that's really where a company like Shiprocket comes in. Now, for those of you maybe unfamiliar, Shiprocket is a titan in the Indian logistics and shipping space, a real leader.
Hmm.
It's essentially a platform designed to empower businesses of all sizes. I mean, from a small artisan selling handmade goods online right up to large e-commerce players, it helps them streamline their entire order fulfillment process.
Yeah, think of it like the ultimate shipping co-pilot for these businesses.
That's a good way to put it. It simplifies everything, right? From the moment an order is booked all the way to its final delivery. It ensures businesses can effortlessly reach customers pretty much anywhere across the country.
And it truly is comprehensive. It's much more than just, a basic shipping tool. It integrates directly with online stores, think Shopify, WooCommerce, Amazon, you name it.
Okay.
It automates the generation of shipping labels, provides real-time tracking for both the business and their customer, and it even manages the often tricky complexities of reverse logistics.
Returns and exchanges. Yeah, that's a big one.
Huge. And on top of that, it also churns out powerful analytics and reports. These give businesses vital insights into their shipping performance, delivery times, costs, even customer satisfaction.
So they can actually see what's working and what's not?
Exactly. All this data helps businesses truly optimize their strategies. The benefits are pretty undeniable. Reduce shipping costs because Shiprocket negotiates rates, increased delivery speed thanks to a wide network, and maybe most importantly, a vastly improved customer experience.
Plus, it sounds like it just simplifies their day-to-day operations and gives them much better visibility into that whole shipping ecosystem.
Precisely. It really is about giving businesses a competitive edge by making their logistics, well, frictionless and intelligent. It's designed to be a complete solution.
Now, for you, our dedicated listener, or maybe you're a curious computer science student, this deep dive is absolutely custom tailored.
Mm-hmm.
You're about to embark on a journey that will take you from being perhaps a curious beginner to someone with an advanced, almost insider's understanding of a Tier 1 logistics platform.
And it's a system I've personally helped design and build right from the initial sketches from scratch.
Exactly. So our mission today is to unpack the entire internal architecture and flow of Shiprocket. We'll be revealing how every single piece, from the fundamental database design choices, the smallest details, right up to the largest cloud services, fits together. How it all works seamlessly to handle literally millions of shipments daily.
And we'll build this understanding piece by piece, just like Shiprocket itself was meticulously built. No detail is too small, no concept too basic to start with.
We're not just scratching the surface here, we are going deep under the hood.
You'll see the intricate design choices, the trade-offs we absolutely had to make, and frankly, the sheer ingenuity required to operate at this kind of scale with such high reliability. It wasn't easy.
Okay then, let's unpack this. To truly understand a system as robust and, frankly, as critical as Shiprocket, we need to move beyond just the what it does and why it exists and dive really deep into the how. We're looking directly into its architectural blueprint. So let's kick off with the executive summary, the core philosophy, really the why behind all the technical hows we're going to get into.
Right. And it's important to stress this isn't just some theoretical design on a whiteboard. This is a practical, production-ready guide reflecting how a Tier 1 logistics aggregator is actually built and run, especially considering the unique operational realities of the Indian market.
Gotcha. So what were those non-negotiable goals from day one?
Well, there were three big ones. First, massive scale. We knew we had to handle millions of shipments daily. We're talking potentially 3 to 5 million during peak seasons. Think Diwali, Eid, the surges are huge in India.
Wow, 3 to 5 million a day.
Per day, yeah. Second, 99.99% availability. 4 nines. That means near perfect uptime. Businesses rely on us for their core operations, so the system just has to be available.
Downtime is just not an option.
Pretty much. And third, uncompromising financial and data integrity. We're managing financial transactions exceeding $50 million monthly. So you absolutely need robust safeguards against any kind of discrepancy or data loss. Trust is paramount.
Okay, those are some serious requirements. So what's the foundation built on to support that? What are the pillars?
All right, so the foundational pillars. First, it's built on a cloud-native, domain-driven microservices paradigm.
Okay, break that down. Microservices.
Right, so the entire system is decomposed into small, independent services. Each one is responsible for a very specific business domain, like order management or label generation or payments. Very focused.
Got it. And cloud native.
Meaning it's designed from the ground up to run in the cloud. Specifically, the exclusive deployment environment is Amazon EKS, that's Elastic Kubernetes Service. AWS is managed Kubernetes. It takes away a lot of the operational burden of running Kubernetes clusters yourself.
Okay, so lots of independent services running on Kubernetes in AWS. How do you manage all that complexity?
That's where the next pillar comes in. An Istio service mesh. This is critical. Istio sits as a layer across the entire ecosystem and governs how services talk to each other. It abstracts away complex infrastructure concerns, things like traffic management, security between services, observability. It handles that, letting the service developers focus purely on the business logic.
Like a control plane for the microservices themselves.
Exactly. And the final pillar is a unified technology stack. This was a deliberate choice for consistency. Every single service, all 27 core service domains, are built using Java 21 with the Spring Boot 3 framework.
Wow, strict standardization.
It simplifies development, makes maintenance easier, ensures consistency, and helps with hiring and onboarding too.
Now, you mentioned this is a final revision of the architecture. That implies it evolved. What kind of things changed or got addressed?
Oh, absolutely. Architecture is never static, especially at this scale. This revision addressed critical gaps we found in earlier versions. For instance, we significantly enhanced the financial ledger architecture. We introduced much more robust reservation management and sophisticated compensating transaction handling.
Compensating transactions, like undoing things if part of a process fails.
Precisely. Essential for financial integrity in a distributed system where failures aren't always all or nothing. We also introduced a gateway per carrier model for integrations.
Okay, what does that mean? Gateway per carrier.
It means instead of one big service handling integrations with all external shipping carriers like FedEx, Blue Dart, etc., each carrier gets its own dedicated, isolated integration microservice, its own gateway.
Ah, so if one carrier's API has problems.
It doesn't bring down the whole system. It minimizes the blast radius, as we call it. Only that specific carrier's integration is affected. We learned that one the hard way, but it's made the system much more resilient.
That makes a ton of sense. Anything else in this revision?
Yeah, more detailed patterns for shard rebalancing and ensuring consistency across database shards, security hardened authentication with refresh token rotation, a complete mapping of the e-commerce platform integration flow, Shopify, Amazon, all those, and really comprehensive failure scenario coverage, backed by operational runbooks.
Amongst, like actual playbooks for engineers when things go wrong.
Exactly. Step-by-step guides for specific failure scenarios. Because things will go wrong eventually, and you need to be prepared.
Okay, that gives a great overview of the philosophy. Let's dig into the specific guiding architectural principles. You called it the Shiprocket doctrine.
Hey, yeah, maybe a bit formal, but these are the laws we build by. The first, and maybe the most fundamental, is domain-driven design, DDD, as law.
DDD as law, meaning?
Meaning, we are rigorous about decomposing the system into microservices that represent clear, unambiguous business domains. Each service aligns precisely with one of Shiprocket's documented service domains. No blurry lines.
It sounds like building with Legos, but maybe Lego technique, where each piece is highly specialized and does one specific job really well.
That's a great analogy. And that strict separation is absolutely key for scalability, maintainability, and organizational agility. Teams can own their domains, develop, and deploy independently without stepping on each other's toes.
Okay, principle number 1, DDD. What's next?
Next up is a clear bifurcation in communication patterns. Synchronous for immediacy, asynchronous for throughput. This isn't just a random choice. It's strategic, based entirely on the nature of the operation.
Okay, so when do you choose synchronous?
For any user-facing, latency-sensitive operation where the user needs immediate feedback, think about creating a single order in the UI or clicking Generate Label. They need a quick response.
Makes sense. And what tech for that?
For internal synchronous communication, we use gRPC. We chose it over traditional REST because, well, it generally offers superior performance. It enforces strict schemas using protocol buffers, which is great for preventing integration issues. And it has native support for streaming, which can be useful.
Okay, faster, stricter internal calls with gRPC. What about asynchronous?
Asynchronous communication via Kafka is reserved for anything high throughput, deferrable, or where you want loose coupling between services. Think bulk order uploads, sending out notifications, feeding analytics data pipelines, or broadcasting events between different domains.
And why Kafka for that?
Kafka provides resilience and allows services to scale independently. It acts as a durable buffer. If a downstream service is slow or temporarily unavailable, Kafka holds the messages, and the upstream services can continue operating without interruption. The downstream service just catches up later. It's fundamental to our event-driven architecture and prevents bottlenecks from cascading.
Right, decoupling is key. This brings us to another really interesting principle. Pragmatic and purpose-fit consistency, final revision. Sounds like you're saying consistency isn't one size fits all.
Exactly. We explicitly reject that idea. We apply the appropriate consistency model to each specific domain, carefully considering the throughput needs and the operational realities. It's about understanding the business requirements deeply.
Can you give an example, like for the really sensitive stuff?
Sure, let's take the finance domain. Obviously super sensitive. Here, we use a hybrid consistency model with built-in safety nets. It's a two-phase approach.
Two phases.
Yeah. First, there's a reservation phase. This uses optimistic locking with versioning for the initial high-throughput hold on funds. It's fast and handles high concurrency well. Then, the settlement phase kicks in for the actual movement of money. Here, we switch to strict serializability with fine-grained locking. We lock only individual ledger entries, not the entire seller account, to ensure absolute financial integrity without killing performance during peak times.
And the safety nets.
Those are the compensating transactions we talked about, coupled with dead letter queue, DLQ handling. If a step in the financial process fails partially, a compensating transaction automatically tries to undo the completed steps. If even the compensation fails, the event goes to a DLQ for manual review by our finance ops team. It ensures we never lose track of money.
Wow, okay, that's robust. What about less critical domains, like just regular business logic?
For the business logic domain, like managing orders which see high throughput, we generally use optimistic locking with conflict resolution. It's version-based, allowing high concurrency. If two updates happen simultaneously, the system detects the conflict based on the version number, and we have sophisticated logic built in to resolve common scenarios, like two updates trying to change the inventory status of the same order line item.
And you mentioned a synchronization domain for things like inventory levels.
Right. For eventually consistent data like cross-channel inventory levels, we use version CRDTs. That stands for conflict-free replicated data types.
Okay, CRDTs. How do they work?
At a high level, a CRDT is a data structure that can be replicated across multiple servers, updated independently on each replica, and then merged back together automatically without conflicts. Critically, we use vector clocks with our CRDTs, not just a simple last right wins approach.
Why vector clocks?
Vector clocks provide a way to precisely determine the causal order of events across distributed systems. This eliminates data loss that can happen with last right wins due to clock skew, where server clocks aren't perfectly synchronized. CRDTs with vector clocks give us strong eventual consistency guarantees with relative operational simplicity.
Fascinating. Okay, moving on. Next principle.
GitOps as the single source of truth. This is all about automation, auditability, and reproducibility.
How does that work in practice?
The entire state of our infrastructure. Kubernetes deployments, Istio traffic rules, monitoring configurations, everything is defined declaratively as code, specifically YAML files stored in Git repositories.
So infrastructure as code, but managed via workflows.
Exactly. All changes go through standard Git workflows, merge requests, peer reviews. Once approved and merged, automated tooling like FluxCD automatically applies these changes to the infrastructure. This ensures every change is audited, version controlled, and we can easily roll back to any previous known good state. It makes the production environment extremely predictable.
Predictable and auditable. Nice. What's next?
Chaos engineering as a discipline. This is huge for us. Reliability isn't something you tack on at the end. It's a core engineering practice from day one.
So you're intentionally breaking things.
In controlled environments, yes. We implement continuous chaos experiments at multiple levels. The application itself, the Istio service mesh layer, and the underlying AWS infrastructure. We inject failures, latency, network partitions, all sorts of controlled chaos to proactively validate that the system is resilient before real failures happen in production.
Finding the weaknesses before they find you.
Precisely. And the last principle, operational completeness as a requirement. This means no service is considered production ready just because the code works.
What else does it need?
Every service must include detailed operational considerations. Clear monitoring dashboards, well-defined alerts, robust failure handling patterns within the code, comprehensive reliability testing strategies, and, as mentioned, detailed runbooks for incident response. It's about building services that are not just functional, but truly operable and supportable in the real world.
That's a very mature approach to engineering. Okay, let's zoom in on the specific tools now. The Unified Technology Stack, Final Enhancement. You said this is the approved list, no deviations.
Correct. No deviations without a formal architectural review. This ensures consistency and manageability across the board.
All right, let's break down the key components. Start with the core application framework.
Sure. The standard is Java 21, Spring Boot 3.2.x, and Spring Cloud 2023.0.0. This provides a really mature, robust ecosystem for building our microservices. We leverage the full Spring Suite Spring Data JPA with Hibernate for database access, Spring for Apache Kafka for reliable messaging, Spring Security for authentication and authorization using JWT and OAuth 2.
And you mentioned a critical enhancement here.
Yes. Spring Retry with exponential backoff for all service-to-service calls. This might sound like a small detail, but in a distributed system, transient network glitches or temporary service unavailability happen. Spring Retry automatically retries these failed calls with increasing delays, preventing a small hiccup from causing a major cascading failure. It adds significant resilience.
Okay, vital little detail. What about the cloud and orchestration layer?
It's all AWS running on Amazon EKS version 1.29 or higher with Docker for containerization. EKS provides managed Kubernetes, giving us scalability and reliability without managing the control plane ourselves. We heavily integrate with other AWS services like IAM for permissions, VPC for networking, and load balancers.
And the critical enhancement for EKS.
As we touched on, the EKS clusters are deployed across 4 availability zones in the App South 1 Mumbai region, not just the standard 3. Node groups are also distributed across these zones. That extra AZ gives us an additional buffer against large-scale infrastructure failures, a belt and suspenders approach for availability.
Makes sense for a critical system. How about the service mesh?
That's Istio version 1.21 plus NERS using Envoy version 1.28 as the sidecar proxy. Istio gives us that centralized, code-free control over traffic management, security like MTLS between all services, resilience patterns like retries and circuit breakers, and deep observability.
And the Istio enhancement?
We configure Istio with adaptive circuit breakers. These aren't static. They automatically adjust their tripping thresholds based on recent historical performance metrics of the downstream service. So if a carrier API starts to slow down intermittently, the circuit breaker intelligently adapts, preventing us from flooding it with requests while it's struggling, thus preventing cascading failures during those sudden spikes.
Very cool. What about the main database for transactional data?
The primary choice is Amazon RDS for PostgreSQL version 16.2 or higher, fronted by PG Bouncer. PostgreSQL gives us that structured ACD-compliant storage we need for core data like orders and financial records. RDS handles backups, patching, and failover.
And the PG Bouncer enhancement?
Right. PG Bouncer connection pooling is configured at the service level. Databases have limits on concurrent connections. PG Bouncer manages a pool of connections, efficiently reusing them for multiple application requests. This prevents our services from overwhelming the database with too many connections during traffic spikes, which is a common bottleneck.
Got it. Do you use other databases?
Yes, selectively. For certain high-throughput, low-latency key-value workloads, like perhaps session data or specific tracking information, we use Amazon DynamoDB. And the critical enhancement there is we use global tables.
Global tables?
DynamoDB global tables automatically replicate data across multiple AWS regions. We use this primarily for disaster recovery, ensuring key data is available even if an entire region goes down. We also have application-level conflict resolution logic for the rare cases of multi-region writes.
Okay. What about caching?
For caching and locking, we rely heavily on Amazon Elasticache for Redis version 7.2 plus ADO running in cluster mode with multi-AZ enabled. Redis is incredibly versatile. We use it for high-performance distributed caching, storing user sessions, implementing rate-limiting logic, and managing distributed locks for operations that need mutual exclusion. Cluster mode gives us scalability and high availability.
And the enhancement for Redis.
Our Redis cluster is configured with 3 shards and 2 replicas per shard, spread across multiple availability zones. This provides both horizontal scaling and high availability. We also conduct weekly automatic failover testing using chaos experiments to ensure the failover mechanism actually works when needed.
Testing the safety net, good idea. The messaging backbone.
That's Amazon MSK, managed streaming for Kafka, version 3.7 plus Kaf band. Kafka is the durable, high-throughput, distributed log for all our asynchronous communication, event sourcing patterns, and feeding data pipelines.
And the enhancement there sounds significant.
It is. Our MSK clusters are configured with 30 brokers spread across 6 availability zones. It's 5 brokers per AZ. This provides extreme resilience against AZ failures. For all critical topics, we enforce a replication factor of 3, meaning every message is safely stored on 3 different brokers across different AZs. Data durability is paramount.
Okay, how do requests get into the system from the outside world, the API entry point?
That's handled by an Istio Ingress gateway, which sits behind an AWS Network Load Balancer, NLB. We also place AWS Way Web Application Firewall in front. The NLB provides the scalable Layer 4 entry point, handling raw TCP connections efficiently. It passes traffic to the Istio Ingress gateway, which handles the smarter Layer 7 routing based on host names, paths, etc.
And the way.
The critical enhancement is using AWS WAF with rate-based rules specifically targeting DDoS attacks on our webhook endpoints. We also have custom rules, for example, to protect payment gateway webhooks from potentially malicious traffic.
Makes sense. Where do you store things like generated shipping labels or documents?
That's object storage, using Amazon S3 with intelligent tiering enabled. S3 is perfect for secure, durable, and infinitely scalable storage for things like shipping labels, PDFs, ZPL files, manifests, seller KYC documents, and also serves as the landing zone for our analytics data lake. Intelligent tiering automatically moves data between access tiers to optimize costs.
Critical enhancement for S3.
We use S3 Object Lock in governance mode for critical financial documents. This prevents accidental dilution of these documents during sensitive periods, adding an extra layer of protection for compliance and audit purposes.
Smart. How about logging? Getting visibility into what all these services are doing.
For logging, we use Fluent deployed as a Kubernetes daemon set on each node. Fluent collects logs from all containers, enriches them with metadata, like pod name, namespace, and forwards them to Splunk, where we use the machine learning toolkit. Splunk provides centralized searching, analysis, and alerting on logs.
And the Splunk ML toolkit.
The critical enhancement is using Splunk's ML toolkit to establish baselines for normal log patterns and automatically detect anomalies. This helps us spot potential issues much earlier, sometimes even before they trigger traditional threshold-based alerts.
Proactive monitoring. Nice. Metrics?
For metrics and monitoring, we use Prometheus, version 2.45 plus, scraping metrics from Istio and our Spring Boot applications via the Micrometer library. Grafana, version 10.1 plus, is used for creating dashboards and visualizing these time series metrics. Additionally, we use Datadog APM.
Datadog APM. What's the critical enhancement there?
Datadog APM gives us distributed tracing with code-level visibility. It helps us identify bottlenecks not just at the service level, but pinpoint slow methods or database queries within a service. This is invaluable for performance tuning across our distributed system.
And you mentioned tracing specifically.
Yes, for distributed tracing, the primary tool is Jaeger, version 1.48 plus, integrated with OpenTelemetry. Istio automatically generates trace spans, and Jaeger stitches them together, providing end-to-end visibility of requests as they flow across multiple microservices. This is essential for debugging latency issues.
The enhancement for tracing.
We use OpenTelemetry instrumentation at the code level for critical financial operations. This allows us to inject specific business contexts like transaction IDs or amounts directly into the trace data. So when we're investigating a financial discrepancy, the trace tells us not just which services were involved, but what specific financial operation was happening.
Very powerful for debugging, testing, and reliability tools.
We use a combination. Chaos Mesh, version 2.5 plus, for Kubernetes native chaos engineering, Locust, version 2.18 plus, for realistic load testing, and Gremlin for more targeted, controlled failure injection experiments.
And the key here is integration.
Absolutely. The critical enhancement is that these tools are integrated into our CI/CD pipeline to automatically run reliability tests before new code reaches production. Reliability testing is part of the definition of done.
Finally, configuration management. How do services get their settings?
We use AWS App Config and AWS Systems Manager Parameter Store for centralized configuration management. The critical enhancement is a dedicated carrier configuration service.
Why a dedicated service just for carrier configs?
Because carrier settings, API keys, rate tables, service rules change frequently and are managed by business operations teams, not just engineers. This service provides a user interface for managing these settings, enforces versioning with full audit trails for every range, includes validation rules specific to each carrier, and allows carrier adapter services to dynamically reload configuration without needing a restart. It makes managing complex carrier integrations much safer and more agile.
Okay, that's a fantastic overview of the tech stack. Let's peel back another layer now and dive into the platform's bedrock, starting with Amazon EKS, the Elastic Kubernetes Service, which you said is the foundation for scale.
Right. So EKS provides the managed Kubernetes control plane. What that really means for you, as someone learning this, is that AWS handles the complex and critical back-end components of Kubernetes. Things like the etc. distributed database that stores the cluster state, the Kubernetes API server itself. They manage its availability, patching, scaling across multiple availability zones.
So you don't have to worry about managing the brain of Kubernetes, just using it.
Exactly. It frees up our teams to focus on deploying and managing our applications, not the underlying orchestration infrastructure. And that control plane is inherently highly available because AWS runs it across multiple AZs.
We talked about the 4 AZ deployment. How does that translate down to the worker nodes where the actual application containers run?
Good question. The multi-AZ deployment extends to the worker nodes too. We configure EKS node groups of EC2 instances that run our pods and distribute these node groups across all 4 availability zones in the Mumbai region. Furthermore, we have different node groups for different tiers of services.
Tiers, like critical versus non-critical.
Precisely. Critical financial services might run on dedicated node groups, separate from, say, reporting services. This isolates workloads and prevents resource contention, a noisy neighbor problem, where one busy service impacts another unrelated one running on the same machine.
Okay, smart isolation. What about managing resources within the pods? CPU, memory.
That's under resource management, and it's non-negotiable. Every single Kubernetes deployment manifest must include precisely defined resource requests and limits for both CPU and memory.
Why is that so strict?
Requests tell Kubernetes how much resource to reserve for the pod, guaranteeing it gets at least that much. Limits prevent a pod from consuming excessive resources and impacting other pods on the same node. Setting these accurately ensures stable performance and predictable scheduling by Kubernetes. Without them, you get unpredictable performance and potential node instability.
How do you handle varying load? Do you just over-provision everything?
No, that would be wasteful. We use horizontal pod autoscalers, HPAs, configured for virtually every service. The HPA automatically monitors metrics, primarily CPU utilization, and scales the number of pods for a deployment up or down based on demand. We typically target around 70% average CPU utilization.
So it automatically adds more instances of a service when load increases and remove them when it decreases.
But there's a critical enhancement.
Right.
We also use vertical pod autoscalers, VPAs, but selectively.
Why selectively? And what do VPAs do differently?
VPAs are deployed primarily for stateful services, like our core account service. These services often have database connections or other stateful characteristics that make simply adding more pods, horizontal scaling less effective or even counterproductive. It might just increase database contention.
Okay.
VPAs, instead of changing the number of pods, monitor the actual CPU and memory usage of existing pods over time. They then recommend or can even automatically apply optimal resource requests and limits for those pods. So it makes the existing pods more efficient, tuning their size vertically.
So HPA changes the number of pods, VPA changes the size of the pods.
You got it. It's particularly useful for those stateful workloads that don't scale horizontally as easily.
You also mentioned isolating critical services using node affinity and paints. How does that work?
We designate specific node groups just for critical financial services. These nodes have a taint applied. A taint prevents general workloads from being scheduled onto them. Then, the deployments for our critical financial services have a corresponding toleration and node affinity rule, which essentially says, I can tolerate this taint, and I prefer, or require, to run on nodes with this specific label.
So it reserves those nodes just for the important stuff.
Exactly. It ensures strict isolation. These dedicated nodes also get enhanced monitoring and are carefully excluded from standard automated maintenance windows to minimize any potential disruption.
What about scaling the cluster itself, adding more nodes?
That's handled by the cluster autoscaler. It watches for pods that can't be scheduled due to resource constraints and automatically adds more nodes to the appropriate node group. But here too, there's a custom enhancement.
What's the customization?
Our cluster autoscaler uses a custom scaling profile. It doesn't just look at CPU and memory requests. It also incorporates other metrics, specifically I/O metrics related to database connection usage from Prometheus.
Why look at database connections for node scaling?
We found scenarios where scaling out application pods based purely on CPU would lead to a surge in database connections that the RDS instance couldn't handle efficiently. By incorporating DB connection metrics into the scaling decision, the cluster autoscaler ensures that we only add nodes if the entire stack, including the database layer, can likely handle the increased load from the new pods. It prevents scaling out from causing a bottleneck downstream.
That's a very sophisticated feedback loop. Okay, let's move on to the Istio service mesh, the control plane for microservices. You said this is fundamental.
Absolutely. The magic of Istio starts with its Envoy proxy sidecar. When we deploy a Spring Boot service pod in Kubernetes, Istio automatically injects this lightweight Envoy proxy container right alongside our application container within the same pod.
So every application pod has its own little proxy.
Yes. And all network traffic going into or out of our application container is automatically intercepted and routed through this Envoy proxy. This is incredibly powerful.
Why? What does that enable?
It means Istio's control plane can manage all service-to-service communication centrally, without requiring any changes to the application code. Things like setting up retries, defining timeouts, enforcing security policies like MTLS, implementing circuit breaking, managing traffic shifting for canary releases, all configured declaratively in Istio YAML files, not coded into each service.
Oh, wow. It's like having a universal translator and traffic controller embedded with every service, handling all the tricky network stuff automatically.
That's a perfect way to think about it. It dramatically simplifies the lives of application developers and provides consistent platform-wide policies.
You mentioned declarative resilience patterns, like those adaptive circuit breakers.
Exactly. The adaptive circuit breakers are a great example. We define an Istio destination rule for a service, say, an external carrier API. Instead of setting a fixed error threshold, we configure it to adapt based on historical performance. If the carrier API suddenly starts failing more often, Istio automatically tightens the circuit breaker threshold, tripping sooner to prevent our system from hammering a failing service and causing cascading failures. It intelligently protects the system's stability.
What about testing new code safely in production?
Istio enables traffic mirroring, also known as shadowing. This is fantastic for testing critical changes, especially in financial services. We can configure Istio to duplicate a percentage of live production traffic and send the copy to a new version of a service deployed alongside the stable version. The mirrored traffic hits the new version, but the responses are ignored. They don't go back to the user.
So you can see how the new version handles real production load and data without any user impact.
Precisely. It drastically reduces the risk of deploying changes to critical systems. We can validate performance and correctness with real traffic before doing a full cutover.
Okay, Istio handles the traffic. What about securing the platform itself? Let's talk about the platform security layer, guardians of the system.
Security is layered throughout, absolutely critical. Let's start with secrets management. How do we handle sensitive things like database passwords, external API keys, certificates?
Yeah, you definitely don't want those floating around in code or config files.
Absolutely not. The solution involves two key AWS services: AWS Secrets Manager for securely storing the secrets, and the AWS Secret Store CSI driver for Kubernetes.
How does that CSI driver work?
We define a Kubernetes resource called a secret provider class. This resource references the specific secrets we need from Secrets Manager. The CSI driver, running on the Kubernetes nodes, securely retrieves these secrets and mounts them as files into the application pods, typically under a directory like men-secrets. Our Spring Boot applications are then configured to read sensitive configuration values directly from these files.
So the application just reads a local file, but the secret itself is managed securely by AWS and never exposed directly in the pod's environment or image.
Exactly. It's much more secure. And the critical enhancement here is automatic secret rotation. We configure rotation policies in AWS Secrets Manager, typically rotating secrets like database passwords every 90 days. Secrets Manager handles the rotation process, often using a multi-step approach, creating a new version, testing it, then marking the old one for deletion, to ensure zero downtime for the application during rotation.
Very neat. What about network security between the services themselves?
That's handled by Kubernetes network policies. We enforce a strict deny by default network posture. This means By default, no pod can talk to any other pod.
Zero trust, basically.
Pretty much. Then for each service, we create a network policy resource that explicitly whitelists the specific inbound traffic that is allowed. For example, the policy for the account service might only allow ingress traffic from the order service and the label service on specific ports, dropping all other connection attempts.
How do you manage creating and updating all those policies for dozens of services? Sounds like a lot of manual work.
It would be, and error-prone. That's why the critical enhancement here is that network policies are automatically generated. We built a custom tool that analyzes the actual service dependency graph, looking at which services make gRPC or REST calls to which other services, and generates the corresponding network policy YAML files.
So the policies always reflect the actual communication patterns?
Yes, and they get updated automatically as part of our CI/CD process whenever dependencies change. It ensures accuracy and significantly reduces the chance of misconfiguration, leading to security holes.
How do services securely access other AWS resources like S3 buckets or DynamoDB tables? Do they use static access keys?
No, definitely not static keys. That's a huge security risk. We use IAM roles for service accounts.
Oh, RSA. How does that work?
Each Kubernetes service account, which is associated with our application pods, is linked to a specific AWS IAM role. When a pod needs to talk to an AWS service, the AWS SDK inside the pod automatically and securely exchanges a Kubernetes token for temporary AWS credentials via an OIDC handshake managed by EKS and IMM.
So the pod gets short-lived AWS credentials without ever needing to store or manage long-lived IAM user keys.
Correct. It's the standard, secure way to grant AWS permissions to applications running in EKS. And the critical enhancement is how we scope these IAM roles. We use AWS IAM Access Analyzer to help us define roles with the absolute minimum required permissions, principle of least privilege. We also apply permission boundaries to prevent any potential privilege escalation.
Okay, very tight controls. You mentioned webhooks earlier, especially from external systems like payment gateways. How are those secured? It sounds like a multi-layered approach.
It has to be. External webhooks are a common attack vector. So our webhook security enhancement involves multiple layers. 1. Signature validation. All incoming webhooks must be signed, typically using HMAC SHA-256 with a shared secret. We validate this signature on every request. The keys are stored securely and rotated frequently, usually every 30 days. 2. Idempotency handling. Network issues can cause webhooks to be sent multiple times. We use our Redis cluster to store idempotency keys provided in the webhook request or derived from it. If we see the same key again within a certain window, we know we've already processed it and can safely ignore the duplicate. 3. Rate limiting. As mentioned, AWS will apply strict rate-based rules to webhook endpoints to mitigate DDoS attacks or abusive clients. 4. Request validation. Before processing any webhook payload, we validate it rigorously against a predefined Avro schema using our schema registry. Invalid payloads are rejected immediately. 5. Automated security testing. We integrate automated security scanning tools like OSPF into our CI pipeline to proactively scan our webhook endpoints for common web vulnerabilities like injection attacks or misconfigurations.
That's a very thorough defense. Okay, last piece in this section. Chaos engineering and reliability practices. You mentioned it's a discipline. How is it actually practiced?
It's embedded in our engineering culture and tooling. The core principle is that reliability isn't just tested at the end, it's continuously practiced. We run continuous chaos experiments at multiple levels. Application level, using libraries or agents to inject faults directly into the service code, things like random thread pauses, throwing exceptions, adding artificial latency to specific methods. Service mesh level, using Istio's fault injection capabilities to simulate network problems between services latency, packet loss, connection resets, HTTP error responses. Infrastructure level, using tools like Chaos Mesh or AWS Fault Injection Simulator to simulate underlying infrastructure failures, terminating EC2 instances, causing AZ outages, inducing database failovers, stressing CPU or memory.
And this isn't just manual.
No, it's largely automated. We have an automated chaos testing pipeline. Experiments are defined declaratively, usually in YAML, stored in Git, GitOps again. They get validated during the CI build process. They run automatically against new code versions in our staging environment. And we even run a subset of safe, well-understood experiments continuously in production during off-peak hours.
How do you know if an experiment passed or failed?
That's the results analysis part. Our monitoring systems, Prometheus, Grafana, Datadog, capture key service-level indicators, SLIs, before, during, and after a chaos experiment. Automated analysis compares these metrics against predefined service-level objectives. SLOs. If the system remains within its SLOs despite the injected failure, the test passes. If SLOs are breached, the test fails, triggering an alert and investigation.
And you mentioned specific experiments for financial services.
Absolutely. The critical chaos experiments for financial services are vital. We must prove that our financial safeguards work under duress. We run experiments specifically designed to simulate database failures, network partitions, or message queue issues during critical financial operations, like payment processing or ledger updates, to rigorously validate that our saga patterns, compensating transactions, and exactly once processing guarantees hold up and prevent data loss or corruption. You simply cannot afford to hope these systems are robust. You have to actively try to break them in controlled ways to be sure.
Okay, we've covered the vision, the principles, the tech stack, and the platform bedrock like Kubernetes and Istio. Now it's time to zoom into the actual microservice architecture, the building blocks of Shiprocket. You mentioned there are 27 distinct service domains.
That's right. Each one is like a specialized expert focused on a specific part of the business. We obviously can't cover all 27 in detail, but we can dive into a few key ones that really demonstrate the important architectural patterns and how we solved specific business challenges.
Sounds good. Where should we start?
Let's begin with a really critical one, the authentication session domain, and specifically the auth service. This one has had some final security enhancements implemented.
Okay, the auth service. What's its core responsibility? Its bounded context.
Its bounded context is crystal clear. It is the single definitive authority for seller identity, handling all aspects of authentication and API access control. It determines who you are and what you're allowed to do. Because of this, it's an extremely critical service, needs very high availability, very low latency. We target that 99.99% uptime for it.
The gatekeeper, basically.
Exactly. It manages logins, validates tokens or other services, issues new tokens, handles refresh tokens, and manages logout and revocation.
What about its API endpoints and gRPC methods? How do others talk to it?
It exposes REST endpoints for external interactions, like V1 external auth login, refresh, and logout. Internally, other microservices communicate with it primarily via gRPC methods like validate token, which is called constantly to verify access tokens, and introspect token for getting more detailed information about a token if needed.
Let's look at the core business logic. How does it actually authenticate a user and manage tokens?
Okay, so 1, authentication. We use Spring Boot Starter security pretty heavily here, configured for JWT JSON Web Tokens. When a login request comes in, a custom user detail service loads the seller's details, usually from the database, and bcrypt password encoder securely compares the provided password hash against the stored hash. 2, JWT generation. If authentication succeeds, we use the io.jsonwebtoken.jwt library to generate JWTs. We include standard claims like subject, which is the seller ID, yes, issuer, the auth service ID, expiration time, typically short, like 15 minutes for access tokens, but also custom claims like roles, audience, and importantly, a JKT, JWT ID, which is a unique identifier for each token used for revocation. Refresh tokens have a much longer expiry, say 7 days, captured in a refreshes claim. 3, token refresh, enhanced security. This is crucial. We implement refresh token rotation. When a client uses a refresh token to get a new access token, that refresh token is immediately invalidated, marked as used or revoked, and the auth service issues both a new access token and a new refresh token. This prevents refresh tokens from being long-lived and reusable if compromised. Each refresh token is essentially single use. 4, token revocation. If a user logs out or a token is suspected compromised, we need to revoke it before its natural expiry. We maintain a list of revoked token JDIS in a Redis cache. The TTL, time to live, for each entry in Redis matches the remaining lifetime of the revoked token. We also use a Bloom filter as a probabilistic check before hitting Redis for potentially revoked tokens, which optimizes performance for high-volume checks. 5, security hardening. Basic but essential stuff like rate limiting on login attempts, you fix 5 attempts per minute per IP address, and account lockout policies, frequently lock account after 10 failed attempts to mitigate brute force attacks.
Okay, that token rotation and revocation piece sounds really important. Where is all this user data and token state stored? The data model and storage.
The primary user data email, password hash, status, etc. is stored in a PostgreSQL database. The user's table has indexes on email for fast lookups. We also use optimistic locking, version column, on the user record.
And the tokens.
The token revocation list, as mentioned, lives in our Redis cluster, keyed by the JT. For managing the refresh tokens themselves, since they need to persist longer and be tracked for rotation, we use another table in PostgreSQL, refresh tokens. This stores a hash of the refresh token, its expiry, seller ID, and whether it's been revoked. We have indexes on Celerid and expire set here.
How do you monitor this critical service? Operational considerations.
We track key metrics very closely. P99 latency for the crucial validate token gRPC call, must be 5 meters, login success and failure rates, token refresh rates, and the rate of refresh token rotation successes. Alerts are configured for any spike in authentication failures, potential brute force, if P99 latency exceeds 10 meters, or if we detect attempts to reuse revoked refresh tokens. And for reliability testing, we run weekly chaos experiments specifically targeting the auth service, like simulating database failures during an authentication attempt to ensure our fallback mechanisms and caching strategies work correctly.
All right, solid foundation for identity. Let's jump to another really crucial area for Shiprocket, platform integration. You mentioned a platform sync service.
Yes, this is a critical service, essentially the bridge between Shiprocket and the outside e-commerce world. Its bounded context is to be the central hub for integrating with all those different e-commerce platforms, Shopify, Amazon, eBay, WooCommerce, Magento, you name it. It's responsible for synchronizing order data into Shiprocket, pushing tracking information back out to the platforms, and keeping inventory levels synced up. Its reliability is absolutely vital for Shiprocket's core value proposition.
How does it handle talking to so many different platforms? The core business logic must be complex.
It is. It uses a few key strategies. 1. Platform connection management. Sellers connect their stores via our UI. We securely store their credentials, API keys, tokens, etc., encrypted in our database. 2. Webhook-based synchronization, preferred. Whenever possible, we rely on webhooks. Platforms like Shopify can push events to us in real time whenever a new order is created or updated. We have internal webhook endpoints, V1 internal webhooks platform type to receive these pushes. This is the most efficient method. 3. Polling-based synchronization, fallback. Not all platforms support comprehensive webhooks. For those, we have fallback polling mechanisms. The service periodically reaches out to the platform's API based on configured frequency to fetch new orders or updates since the last poll using cursors or timestamps. 4. Order normalization. This is a huge part of its job. Every platform sends order data in a slightly different format. The platform sync service takes this varied input and translates it into Shiprocket's standardized internal order model. This ensures consistency for all downstream services like the order service. 5. Tracking information pushback. Once a shipment gets a tracking number and updates from our tracking service, Platform Sync is responsible for pushing this information back to the original e-commerce platform so the end customer can see the tracking status in their Shopify or Amazon account. 6. Inventory synchronization. It also plays a role in keeping inventory levels consistent between Shiprocket, if managing inventory, and the connected sales channels.
Where does it store connection info and sync status, data model, and storage?
It uses PostgreSQL. Key tables include platform connections, storing seller ID, platform type encrypted credentials, sync status, last sync cursors, etc. Platform connection failures, tracking delivery status to track pushes, inventory sync status, and a table to log incoming platform webhook events. We have indexes, particularly a composite index on Celerid, platform type, status, for efficient querying.
And operational considerations for syncing.
Key metrics include the success rate of establishing connections, the latency of order synchronization from platform event to order created in Shiprocket, the success rate of pushing tracking info back, and the accuracy of inventory sync. We have alerts if the connection failure rate spikes above, say, 5%, or if the tracking push failure rate goes above 1%. For reliability testing, we run daily chaos experiments simulating failures in external platform APIs to ensure our polling fallbacks, retry mechanisms, and error handling work correctly.
Okay, that sync service sounds vital. Let's move into the domain that absolutely cannot fail. Finance, the heart of trust. Let's talk about the account service, the financial ledger. This sounds like the most critical piece.
It arguably is. Its bounded context is simple but profound. It is the definitive single source of truth for all seller funds, wallet balances, prepaid credits, COD remittances. Its absolute top priority is consistency. Availability and performance are secondary, although we've made significant architectural improvements to ensure it can still handle very high throughput, especially during settlements.
How do funds get into the wallet in the first place? Let's say from a payment gateway recharge.
Right. The payment service handles the interaction with the payment gateway. Once a payment is confirmed successful, the payment service produces a message to a Kafka topic, let's call it wallet recharges. The account service has a Kafka listener consuming from this topic. Critically, this listener uses manual acknowledgement mode.
Manual ACK, meaning
the consumer explicitly tells Kafka when it has successfully processed the message. The entire processing logic within the account service, validating the message, updating the seller's balance in the database, is wrapped in a single database transaction. Only if the database transaction commits successfully does the service acknowledge the message to Kafka. This, combined with Kafka's transactional capabilities, gives us exactly once processing semantics. We guarantee that a wallet recharge message credits the seller's account exactly once, never 0 times or multiple times, even if failures occur.
That's a strong guarantee. Now, the core architecture of this ledger, you mentioned it's a hybrid ledger architecture.
Yes, this is the final production implementation designed for both consistency and throughput. First, it's sharded by seller ID. The entire ledger isn't one giant database table. It's logically and physically partitioned based on the seller ID. Each shard, which might be a separate database instance or schema, handles a subset of sellers. We use consistent hashing to assign sellers to shards, and we have mechanisms for dynamic rebalancing if some shards become hotter than others.
Okay, sharding for scale. What about the consistency model within a shard?
This is where the two-layer consistency model comes in. One, reservation layer. For operations that need to temporarily hold funds, like when generating a shipping label, you need to ensure the seller has the balance before committing to the carrier. We use a high-throughput reservation layer based on optimistic locking with versioning. A reservation is created quickly, holding the funds. These reservations are typically time-bound, e.g. valid for 24 hours, and automatically reversed if not explicitly captured. 2. Settlement layer. For the actual permanent movement of funds, capturing reserve amount, processing a refund, settling a SATA payment, we use the settlement layer. This layer enforces strict serializability using fine-grained locking, but only on the specific individual ledger entries being modified, not the entire seller account balance row. This provides the highest level of consistency for the actual money movement while still allowing concurrency on unrelated transactions for the same seller.
And you mentioned safety nets again. Compensating transactions and DLQs?
Yes, absolutely critical here. If a complex financial operation involving multiple steps fails midway, the system automatically triggers predefined compensating transactions to attempt to roll back the already completed steps. For example, if we capture funds but fail to update an external system, a compensating transaction would reverse the capture. If a compensating transaction itself fails, which is rare but possible, the event is routed to a dedicated dead letter queue, DLQ.
And what happens to things in the DLQ?
The DLQ is monitored closely by our financial operations team. They manually investigate each failed compensation, determine the root cause, and perform the necessary corrective actions to ensure the ledger remains 100% consistent. It's the ultimate safety net for financial integrity.
This sounds very much like implementing the saga pattern for distributed transactions.
It absolutely is. The whole reserve capture flow, combined with compensating transactions and the potential for manual intervention via the DLQ, is a practical implementation of the saga pattern tailored for high-stakes financial operations. For instance, consider partial failure handling. If a payment succeeds and funds are reserved, but the downstream label generation fails, the reservation isn't immediately captured. After a timeout, say 30 minutes, a scheduled job or event triggers the automatic reversal of that reservation via a compensating transaction. The seller's balance is restored.
How do you audit all this?
Every single financial operation, successful or compensated, publishes a detailed event to a dedicated financial events Kafka topic. This topic serves as an immutable audit log. We also have a dedicated reconciliation service that consumes this stream and runs hourly checks against other system data to ensure everything ties out.
Okay, the data model and storage, still PostgreSQL.
Yes, Amazon RDS for PostgreSQL, but implemented with application-level sharding based on Celerite. We have multiple RDS instances, each acting as a shard.
Application-level sharding. How does the application know which database instance to talk to?
We have a component, typically a Spring Bean, acting as a data source router, that inspects the Celerite associated with the current operation. Based on the Celerite and our consistent hashing logic, it routes the database connection request to the correct physical RDS instance, shard, for that seller. Each shard also has its own read replicas for scaling non-critical reads.
What does the schema look like?
Key tables include accounts, storing Celerite, available balance, reserve balance, captured balance, and crucially a version column for optimistic locking in the reservation layer. Reservations, tracking details of temporary holds, transactions, logging actual fund movements, transaction ledger, the detailed immutable log of all debits credits, compensating transactions, tracking rollback attempts, and compensating transactions DLQ for those ultimate failures needing manual review.
And operational considerations for the ledger.
We monitor metrics like DB transaction time for balance updates should be extremely fast, deadlock counts should be near zero, the rate of reservation expirations, reconciliation discrepancy rates must be zero or investigated immediately, and the processing time for items landing in the DLQ. Alerts are critical. PagerDuty alerts fire immediately for deadlocks, any hint of a negative balance, reconciliation discrepancies exceeding a tiny threshold like 0.01%, or a significant backlog in the DLQ. Reliability testing involves daily chaos experiments, simulating database failures or network issues during financial operations to rigorously test the Saga compensation logic and the shard failover mechanisms.
Wow, that's an incredibly detailed look at ensuring financial integrity. Let's shift gears now to the core logistics and fulfillment domain. This is about actually getting the packages moving. Where should we start here? Maybe the courier service. You mentioned that gateway per carrier model.
Yeah, the courier service is central to integrating with the outside world of shipping carriers. Its bounded context is the comprehensive management system for everything related to carriers, their capabilities, their dynamic rate calculation, their serviceability, which PIN codes they cover, and managing the actual technical integrations with their APIs. We handle 15-plus major carriers in India, and their APIs are all wildly different.
Okay, so the core business logic uses this gateway per carrier implementation. Break that down again. How does it work structurally?
Instead of having one massive service trying to talk to FedEx, Blue Dart Delivery, Ecom Express, etc., all with different APIs and authentication methods, we use a carrier adapter pattern with service isolation. One, there's the main courier service. It acts as the central orchestrator, responsible for routing requests, aggregating responses, and service discovery. One, there's the main courier service. Two, then for each carrier, we have a separate dedicated microservice, a carrier adapter service. So there's a FedEx adapter service, a Blue Dart adapter service, and so on. Each adapter knows how to talk only to its specific carrier's API.
So the main courier service doesn't talk directly to FedEx.
No. If a request comes in asking for rates for a shipment, the courier service uses service discovery via Istio's service registry to find all the available healthy carrier adapter services, like FedEx, Blue Dart. It then fans out requests to each relevant adapter in parallel.
And what does each adapter do?
The carrier adapter service implementation is specific to that carrier. The FedEx adapter service, for example, takes Shiprocket's internal request format, translates it into the specific XML or JSON format FedEx's API expects, handles FedEx's unique authentication requirements, makes the call, gets the response, and translates it back into Shiprocket's standard internal format before sending it back to the main courier service.
That modularity sounds great for managing complexity and isolating failures. You also mentioned a carrier configuration service.
Yes, this was a critical enhancement. Managing carrier API keys, account numbers, rate tables, service rules. This often needs to be done by our business operations or carrier relations teams, not just engineers. So we built a dedicated service with a user interface that provides a structured way for them to manage all these carrier-specific settings.
What features does it have?
It supports version configuration, so every change is tracked with a full audit trail. Who changed what, when. It includes validation rules to prevent typos or invalid settings. In Gaelic, a FedEx account number looks like a valid FedEx account number. And importantly, the carrier adapter services can dynamically reload their configuration from this service without needing a restart, allowing for rapid updates.
So the main courier service gets responses back from multiple adapters. Then what?
It performs response aggregation and caching. It gathers all the rate and estimated delivery time, EDD, responses from the different adapters, sorts them based on criteria like cost or speed, and presents the options to the user, or an automated selection logic. It also heavily caches these rate serviceability responses in Redis with a short TTL, maybe 5 minutes, because querying carrier APIs for rates can be slow and expensive. The cache keys are carefully constructed to include all relevant parameters like pickup delivery PIN codes, shipment weight, dimensions, and C flag.
Does it also monitor the health of these external carrier APIs?
Continuously. The carrier health monitoring component constantly probes carrier APIs or analyzes recent success failure rates. If it detects degradation in a specific carrier's API performance, it can automatically adjust the timeouts and circuit breaker thresholds in Istio for that specific carrier's adapter, or even temporarily downweight that carrier in the selection logic.
Proactive adaptation. Where is carrier metadata stored? Data model and storage.
The core carrier definitions, static rate tables, if any, base serviceability rules, and the configuration versions from the carrier config service are stored in PostgreSQL. The dynamic, frequently accessed rate and serviceability responses are cached in Redis using an LRU, least recently used, eviction policy.
And operational considerations for carriers.
We monitor metrics like P99 latency and error rate per individual carrier API. This is key. We need to know if FedEx is slow, not just if carriers are slow. We also track overall carrier API uptime and how often we have to rely on fallback logic. Alerts trigger if the error rate for any single carrier spikes above, say, 10% for 5 minutes, or if their API uptime drops below 99.5%. Reliability testing involves daily chaos experiments, specifically targeting carrier API failures, making an adapter return errors or high latency to ensure our fallback logic, caching, and adaptive circuit breakers function correctly.
Okay, that gateway model makes a lot of sense for managing external dependencies. What about actually creating the shipment label itself, the label service?
Right, the label service is where the actual commitment happens. It's the transactional endpoint for fulfillment. Its bounded context is handling that final booking step with the chosen carrier and generating the physical or digital shipping label with incredibly robust failure handling built in.
So the core business logic for label generation, you mentioned it uses a saga pattern with complete failure handling. Walk me through that.
Absolutely. Generating a label isn't a single atomic operation in a distributed system. It's a multi-step process, a saga. 1. Initiate. The process starts, often triggered by the order service or a user action. 2. Lock. We acquire a distributed lock using Redis on the unique shipmented, with a short TTL, maybe 5 minutes, to prevent multiple concurrent attempts to generate a label for the same shipment. 3. Reserve funds. We make a synchronous gRPC call to the account service to place a reservation on the seller's balance for the estimated shipping cost. This ensures the funds are available before we talk to the carrier. 4. Call carrier API. We make a call via the appropriate carrier adapter service to the chosen carrier's API to actually book the shipment and request the label data. 5. Capture funds. If the carrier API call is successful and returns a tracking number, we make another gRPC call to the account service to capture the previously reserved funds, making the charge permanent. 6. Save label. We receive the label data, example, PDF or ZPL format, from the carrier adapter and save it securely to Amazon S3 7. Update shipment record. We update the shipment record in our database, PostgreSQL, with the tracking number, the S3 path to the label, and set the status to label generated or similar. 8. Release lock. Finally, we release the distributed lock.
Okay, that's a lot of steps. What happens if something fails midway? Say, the carrier API call fails after the funds have been reserved.
That's where the compensating transactions kick in. Each step in the saga has a corresponding undo action defined. If step 4, call carrier API, fails, the saga coordinator triggers a compensating transaction that calls the account service to reverse the fund reservation made in step 3. The shipping status is marked as failed, the lock is released, and the user is notified. The system is left in a consistent state.
So the saga ensures either all steps succeed or the effects of completed steps are undone.
Precisely. We also enforce idempotency handling strictly. Every request to initiate the label generation saga includes a unique idempotency key. If the label service receives the same request twice, maybe due to a network retry, it recognizes the key and ensures the saga doesn't execute a second time, preventing duplicate labels and charges.
Where does the label service store its state? Data model and storage.
It uses PostgreSQL, again sharded by Celerid, just like the order and account services. The main table is shipments, storing the ordered tracking number, current status, the label's 3-path, carrier, version for optimistic locking, timestamps, etc. We have indexes, particularly a composite index on Celerid status created dat for common queries.
And operational considerations.
Key metrics are the label generation success rate per carrier, the P99 latency for the main generate label API endpoint, and crucially, the rate at which compensating transactions are executed, which indicates partial failures. Alerts trigger if the generation failure rate exceeds 1% overall, or if the compensating transaction rate spikes above, say, 0.1%. Reliability testing involves daily chaos experiments that simulate failures at each individual step of the saga, making the fund reservation fail, making the carrier API call fail, making the S3 save fail to ensure the compensating logic correctly handles all partial failure modes.
That's incredibly thorough. Let's briefly touch on a few other critical services in this domain before moving on. You mentioned an NDR management service. What's NDR?
NDR stands for non-delivery report. In the Indian market, unfortunately, the rate of failed delivery attempts can be higher than in some other regions due to various factors like complex addresses or cash-on-delivery issues. The NDR service is a specialized domain critical for India. Its bounded context is handling these failed deliveries efficiently.
How does it work?
It consumes shipment events from Kafka, specifically listening for events indicating a failed delivery attempt. For example, shipment.undelivered. When it detects one, it creates an NDR case. It then uses a sophisticated automation engine with configurable rules to decide the next action, automatically reschedule delivery, attempt redirection to a different address, initiate return to origin, RTO, or notify the seller to provide instructions. It also integrates with our Sense ML intelligence service to get an RTO prediction score, helping prioritize actions on shipments likely to be returned anyway.
So it automates handling of delivery exceptions.
Exactly. It significantly reduces manual effort and helps improve delivery success rates or speeds up the return process.
And the Sense service itself, what does that do?
The Sense service is our internal machine learning intelligence platform. Its bounded context is providing predictive analytics and intelligence scoring. Its main functions are 1. RTO prediction model. Predicts the likelihood of a shipment being returned to the origin before the first delivery attempt is even made. It uses historical data, real-time features, runs on TensorFlow serving, and uses continuous online learning. 2. Address quality scoring. Analyzes shipping addresses using geospatial data and NLP to assign a confidence score, 0-100, indicating the likelihood of successful delivery based on the address quality. 3. MCP, multi-step control process. An experimental NLP interface allowing users to make complex requests in natural language, which Sense then breaks down into a series of orchestrated API calls to other Shiprocket services.
So Sense provides the smarts for things like NDR and potentially address validation.
Correct. Use a PostgreSQL for metadata, S3 for storing trained ML models, and Redis as a real-time feature store. We monitor model accuracy, AUC, ROC for RTO, and prediction latency closely.
One more. How do sellers get onto the platform in the first place?
That's handled by the seller onboarding and KYC service. Its bounded context is managing the entire seller registration and verification process. It uses a state machine, registered, email verified, FACSEPT, KICA approved, active, to track progress. It handles email verification, collecting KYC, know your customer documents, and integrating with third-party services to verify information like GST numbers and bank accounts, ensuring regulatory compliance. It uses PostgreSQL to store seller details and KYC status.
Okay, that covers a lot of the core building blocks. All right, let's shift focus now to how all these services talk to each other asynchronously and how data flows for analytics. This is part 4, Data and Eventing Architecture, Deep Dive, the Central Nervous System.
Exactly. And the absolute heart of that nervous system, as we've mentioned, is our Kafka topic architecture, which has been enhanced with exactly one semantics for critical flows. Kafka is the backbone for almost all asynchronous communication between our microservices.
And you use Avro for schemas?
Yes. We use Avro for defining the structure of messages on Kafka topics. We have a central schema registry, like Confluent Schema Registry, where all Avro schemas are stored and versioned. Critically, we enforce schema compatibility checks. This means a producer can't update a schema in a way that would break existing consumers. It ensures data contracts are respected across the system.
Okay, there are about 15 core Kafka topics listed in the architecture. Rather than list every single one, can you maybe highlight the patterns of communication and give examples of the most critical topics and why they use exactly once?
Sure. The patterns generally fall into a few categories. Commands. One service telling another to perform an action. For example, platform sync commands. Events. One service notifying others that something significant has happened. Example, shipment events, orders created, financial events. Data synchronization. Propagating changes in data between services. For example, normalized orders, normalized inventory updates.
And the exactly once semantics. Why is that so vital and how is it implemented?
It's exactly. Once semantics, EOS, is absolutely paramount for any topic carrying financial data, order state changes, or inventory updates anywhere where processing a message 0 times or multiple times would cause serious data inconsistencies or financial errors. We implement it using Kafka's built-in transactional capabilities. Kafka transactions. We enable transactions on the Kafka brokers themselves, producers. Our Spring Kafka producers are configured to use transactions. Spring.kafka.producer.transaction e-prefix. They send messages within a transaction, which is only committed if the producing service's own operation, like a database update, succeeds. Consumers. Our Spring Kafka consumers are configured with isolation level, read committed. This means they will only read messages that were part of a successfully committed Kafka transaction from the producer. They also participate in the transaction by committing their offsets within the same transaction that processes the message. This atomic commit of message processing plus offset update is what guarantees exactly once delivery from Kafka's perspective.
So it's a coordinated effort between broker, producer, and consumer. Can you highlight a few specific topics where EOS is non-negotiable?
Absolutely. Wallet recharges. produced by the payment service, consumed by the account service. EOS prevents double crediting or missing a wallet top-up. We retain this for 30 days. Partitioned by seller-rid financial events. Produced by the account service after any ledger change, consumed by reconciliation and analytics. EOS ensures a perfectly accurate, auditable financial trail. Retained for 90 days for audit, partitioned by seller-rid normalized orders. Produced by platform sync, consumed by order service. EOS ensures an order is created exactly once from an incoming platform event. Retained 7 days. Partitioned by seller-rid.shipment events. Produced by tracking service, consumed by NDR, returns, notifications. While maybe slightly less critical than finance, EOS here prevents duplicate NDR cases or return requests being triggered. Retained 7 days. Partitioned by shipmented compensating transactions. Used internally by various services to trigger rollback actions via dedicated service. EOS ensures a compensation request is processed exactly once. Retained 7 days. Partitioned by seller-rid.
That's a really robust eventing system. How do you get data out for broader analytics without hammering the production databases, the analytics data pipeline?
Right. We need to feed our data warehouse and analytics tools, but running complex analytical queries directly against the production system, PostgreSQL or DynamoDB databases, would kill their performance. So we use change data capture, CDC.
CDC, capturing database changes. How?
The process starts with Debezium, an open-source distributed platform for CDC. We run Debezium connectors within a dedicated, highly available Kafka Connect cluster, 3 instances for HA. These connectors are configured to monitor the transaction logs, WAL write-ahead logs, of our production PostgreSQL databases.
So it reads the database's internal change log.
Exactly. Debezium captures every row-level change, insert, update, delete as it happens, transforms it into an Avro event, and publishes it to corresponding Kafka topics. Example, a topic for orders changes, one for shipments changes, etc. We've enhanced our Debezium setup with DLQs for failed CDC events, automatic recovery configurations, and robust handling for schema evolution in the source databases.
Okay, so raw database changes are now flowing into Kafka. What happens next?
These raw CDC events then flow into a data transformation layer built using Kafka Streams applications. These stream processing apps consume the raw CDC topics, perform necessary transformations like joining data from different change streams, cleaning data, maybe masking sensitive fields, handle deduplication using event time processing and watermarks, and produce cleaned, business-friendly events to derived Kafka topics.
Getting the data ready for the lake?
Precisely. The next step is data lake ingestion. We use the Kafka Connect S3 sync connector. This connector consumes the transformed Kafka topics and efficiently writes the data as Parquet files into our Amazon S3 data lake, partitioning the data typically by date for efficient querying later. We optimize for file size, around 128 MB target, and use checkpointing for exactly once delivery guarantees to S3.
Data is in the lake. How does it get into the warehouse for dashboards?
We use AWS Glue ETL, extract, transform, load jobs. These glue jobs read the Parquet files from S3, apply further transformations to structure the data into dimensional models, facts and dimensions, suitable for analytics, perform data quality checks, and load the results incrementally into our data warehouse, which could be Redshift, Snowflake, or even queried directly from S3 using Athena.
And finally, how do users access the analytics?
The analytics service provides a REST API endpoint for internal dashboards or reporting tools to query the data warehouse. It implements features like query caching using Redis to speed up common reports and rate limiting to protect the warehouse from excessive load.
That's a really solid pipeline from production DB to analytics. Last topic in this section, shard management and rebalancing. You mentioned the account service and others are sharded. How is that managed?
Right. Sharding is essential for scaling our transactional databases beyond the limits of a single instance, especially for tenant-based data like ours. Our sharding strategy overview has a few layers. Logical sharding. Primarily by seller-rid. All data for a given seller resides within the same logical shard. Physical sharding. While many sellers might share a physical database instance, shard, very high-volume sellers might be migrated to their own dedicated database instance to ensure performance isolation. Shard assignment. We use a consistent hashing algorithm to map seller-rids to physical shards. This minimizes data movement when shards are added or removed.
What happens if one shard gets much busier than others? Do you rebalance?
Yes, that's the shard rebalancing process. This is a critical enhancement for long-term scalability. We have background jobs that monitor shard load, CPU, storage, transaction volume. During off-peak hours, these jobs can automatically initiate the process of moving specific sellers and all their associated data from a hot shard to a less loaded shard. This is done carefully in batches, ensuring minimal disruption.
How do you handle consistency if a single operation, say a transfer between two sellers, involves data on different shards? Cross-shard data consistency.
That's one of the main complexities of sharding. We handle this through several mechanisms depending on the operation. Two-phase commit, 2PC, avoided where possible. While 2PC guarantees atomicity across shards, it's complex and impacts availability. We generally avoid it for high-throughput paths. Saga pattern. For many cross-shard operations, we use the saga pattern we discussed earlier. Each step operates on its local shard, and compensating transactions are used to roll back if any step fails. This prioritizes availability over immediate consistency, asynchronous replication reconciliation. For less critical data, we might rely on asynchronous updates between shards with eventual consistency guarantees, backed by robust reconciliation jobs that detect and fix any discrepancies later. Coordinator service. Sometimes a dedicated coordinator service might be used to manage the state of a transaction spanning multiple shards, ensuring it eventually completes or rolls back consistently.
So different strategies depending on the consistency requirements of the specific cross-shard operation.
Exactly. It's about choosing the right tool for the job, balancing consistency, performance, and availability.
Okay, we've seen the architecture, the data flows. Now let's talk about keeping it all running smoothly. Part 5. Operations and lifecycle management, keeping the engines running. How does code get deployed, and how are problems handled?
This is where the rubber meets the road for reliability. Let's start with the CI/CD pipeline. Ours is heavily based on GitOps principles with reliability testing baked in at every stage. The goal is fully automated deployment that is safe, fast, consistent, and proven to be reliable before it hits production.
Walk me through the process. Developer finishes coding a feature, then what?
Okay. 1. Code commit. Developer pushes their code to a feature branch in GitLab. 2. Merge request in CI. They open a merge request. This automatically triggers our extensive GitLab CI pipeline. This isn't just unit tests. It includes 2. Merge request in CI. Unit tests, JM and Mockito for mocking dependencies. 2. Merge request in CI. Integration tests, using test containers to spin up real DBs, Kafka, etc. 2. Merge request in CI. Static code analysis, Sonar Group checking for bugs, vulnerabilities, code smells against strict quality gates. 2. Merge request in CI, security scan, OSSPs, AP, or similar tools scanning for common web vulnerabilities. 2. Merge request in CI, load testing, running locus scripts against key endpoints to ensure performance doesn't regress, maybe simulating 10,000 RPS peak for critical services. 2. Merge request in CI. Chaos testing, running predefined chaos mesh experiments against the service in the pipeline environment to check basic resilience.
Wow, that's a lot just in the CI phase.
It has to be. Only if all those checks pass does the pipeline proceed. 3. Build and push. A successful build uses Spring Boot's build image command with Mockito build packs to create a lean, optimized OCI-compliant container image. This image is tagged, beginning with the git commit hash, and pushed to Amazon ECR, Elastic Container Registry. 4. Update manifest, GitOps trigger. The CI pipeline then automatically commits an update to a separate Git repository, our configuration repo. It updates the Kubernetes deployment.yaml file for that service, changing the image.tag to the newly built and pushed image tag.
So the code change triggers an image build, which triggers a config change in Git.
Precisely. And that commit to the config repo is what triggers the deployment tool. 5. Staging deployment, FlexCD. We use FlexCD, a GitOps controller running in our Kubernetes clusters. It constantly monitors the config Git repo. When it sees the updated deployment.yaml, it automatically applies that change to our staging environment.
What happens in staging? More tests.
Yes. Once deployed to staging, a suite of automated end-to-end tests runs against the integrated environment. We also run more comprehensive performance benchmarks and execute a wider range of critical chaos experiments against the new version in staging.
Only if it passes all that does it go to production.
Correct. Staging validation is mandatory. 6. Production deployment. After manual approval, based on staging results, the change is promoted to the production configuration branch in Git. FlexCD picks it up for production, but we don't just roll it out everywhere immediately. We use a canary deployment strategy managed by Istio.
Canary deployment, how does that work?
Istio is configured to initially route only a small percentage of live production traffic, say 5%, to the pods running the new version. The remaining 95% still goes to the old, stable version.
And you watch it closely.
Very closely and automatically. Our monitoring systems automatically compare key metrics, error rates, latency, saturation, between the canary, new version, and the baseline, old version. If the canary's metrics are healthy and within acceptable deviation for a set period, Istio is automatically configured to gradually increase the traffic percentage to the new version, maybe 25%, 50%, then 100%.
What if the canary metrics look bad?
Automatic rollback. If the canary metrics degrade significantly for geo rate spikes, the automated system immediately tells Istio to shift all traffic back to the old version, and the deployment is rolled back. Alerts are fired, and the release is investigated. This automated, metrics-driven canary release process drastically reduces the risk of bad deployments impacting users.
That GitOps flow with integrated testing and automated canary releases sounds incredibly robust.
Okay.
But what happens when, despite all that, something does go wrong in production? You mentioned comprehensive operational runbooks.
Yes, because failures will eventually happen in complex systems. Runbooks are predefined step-by-step guides for how engineers should respond to specific incidents. They aim to make incident response faster, more consistent, and less stressful.
Can you walk us through an example? Let's take that scenario. Carrier API latency spike, maybe for FedEx, like you mentioned earlier. How would the runbook guide the response?
Okay, a common scenario. The runbook would detail these phases. Detection, automated. Detection, automated. An alert manager alert fires. This is triggered by a Prometheus query like histogram quantile, 0.99. Some rate Istio request duration milliseconds, bucket destination service, FedEx adapter service 5 meters by 5,000, meaning the 99th percentile latency to the FedEx adapter has exceeded 5 seconds over the last 5 minutes. Detection, automated. The alert is automatically enriched by our observability platform, perhaps linking to relevant Jaeger traces showing slow spans to FedEx. Detection, automated. The alert is routed to the on-call engineer via pager duty. Diagnosis, step-by-step guidance from the runbook. 1. Check Grafana. Open the predefined dashboard for the FedEx integration. Look at the Istio outlier detection panel as Istio actively ejecting FedEx instances from the load balancing pool due to failures. Check overall latency and error rate graphs. 2. Check Jaeger. Find recent traces for requests involving the FedEx adapter. Are the slow spans primarily network latency, time spent waiting for the FedEx API server, or internal processing within our adapter? 3. Check Splunk.
Query logs for the FedEx adapter service and the main courier service for specific error messages or warnings related to FedEx around the time the alert fired. 4. Verify scope. Is the latency affecting all FedEx API endpoints we use, rates, labels, tracking, or just one specific type? 5. Check carrier status. Look at our internal carrier health dashboard. Are other services also reporting issues with FedEx? Check external sources like Down Detector or FedEx's official status page if available. Immediate mitigation, actions to take NW guided by the runbook. 1. Traffic shaping, if localized. If the issue seems transient or affects only a small part, the runbook might suggest temporarily adjusting Istio's circuit breaker threshold for FedEx to be slightly more lenient, or adjusting retry policies via Istio virtual service updates. 2. Feature toggle, if severe. If FedEx is critical but partially failing, the runbook might guide disabling specific non-essential features that rely on FedEx via a feature flag managed in AWS app config. 3. Traffic routing, if widespread.
If FedEx is broadly unusable, the runbook instructs how to use Istio's weighted routing, virtual service, to shift traffic gradually away from the FedEx adapter service towards alternative carriers that serve the same routes, minimizing customer impact. Root cause analysis, post-mitigation. Root cause analysis, post-mitigation. 1. Analyze detailed metrics from the carrier adapter and Envoy proxy. Was it network RTT, DNS resolution, TLS handshake, or server processing time? Root cause analysis, post-mitigation. 2. If server-side, contact FedEx support with specific trace IDs, timestamps, and error details. Root cause analysis, post-mitigation. 3. If network related between AWS and FedEx, engage the internal networking team or AWS support. Root cause analysis, post-mitigation. 4. Review recent deployments or configuration changes related to the FedEx integration. Long-term prevention, follow-up actions. Long-term prevention, follow-up actions. 1. Could we implement more sophisticated adaptive circuit breaking or smarter fallback logic? Long-term prevention, follow-up actions. 2. Do we need to add additional fallback carriers for better redundancy? Long-term prevention, follow-up actions.
3. Can we enhance monitoring to detect a specific degradation pattern earlier? Long-term prevention, follow-up actions. 4. Schedule regular chaos experiments, specifically simulating FedEx API latency or errors. Post-mortem requirements. The runbook mandates a post-mortem for significant incidents, documenting the timeline, quantifying business impact, instantly delayed shipments, failed orders, identifying contributing factors, defining clear action items with owners and deadlines, and importantly, updating this very runbook with any lessons learned.
That is incredibly detailed. It really shows how you operationalize reliability. That detailed runbook example perfectly illustrates the operational rigor. Now let's dive deeper into how that reliability is built and validated before things go wrong. Part 6. Comprehensive Reliability Testing Framework. Building confidence.
Right, this isn't just about testing functionality. It's about actively trying to find the breaking points and ensuring the system behaves gracefully under stress and failure. Our reliability testing strategy uses a multi-level approach.
Multi-level.
We test reliability at different granularities, unit level. Within the code itself, critical paths include unit tests specifically for failure scenarios. We mock dependencies, like databases or other services, to simulate errors or timeouts and assert that the code handles these exceptions correctly. RAOG catches the exception, returns a fallback, retries appropriately. Service level. For each individual microservice, we run isolated chaos experiments using tools like Chaos Mesh, injecting faults like pod kills, network latency, or dependency failures. We also perform targeted load testing to identify performance bottlenecks within that specific service. System level. This involves end-to-end testing across multiple services. We run more complex chaos experiments simulating scenarios like an entire availability zone failure or a network partition between critical services like the order service and account service to see how the entire system reacts and recovers. We test cross-service dependency failures. Production level. As discussed in CI/CD, this includes controlled chaos experiments during off-peak hours and analyzing the reliability metrics of canary deployments with an automatic rollback if necessary.
Okay, that's a thorough strategy. Let's get into the detailed reliability testing implementation. How do you do load and stress testing?
We use Locust for simulating realistic user behavior via HTTP requests and sometimes custom Java clients for testing our internal gRPC services directly. The test scenarios are designed to mimic real-world peak conditions and potential stress points. Peak holiday traffic. Simulating maybe 10x our normal daily load across all core APIs, order creation, label generation, tracking, seller onboarding spikes, simulating a sudden influx of new sellers registering and verifying, for e.g. 100 new signups per minute, bulk order imports, simulating large sellers uploading huge files of orders concurrently, for example, 10,000 orders per minute via the bulk API, payment processing peaks, simulating bursts of wallet recharges during promotional events, for example, 5,000 payment initiations per minute.
What are you measuring during these tests?
We track a wide range of metrics. Obviously, the application-level error rate, latency percentiles, P50, P90, P99, but also system resource utilization, CPU, memory, network I/O on pods and nodes, database connection pool saturation, Kafka consumer lag, Redis latency, and connection counts.
And what defines success? The pass-fail criteria.
The criteria are strict and depend on the service, but generally, error rate must stay below a very low threshold, e.g. 0.1% at the target load. P99 latency should not degrade beyond a certain factor, Koji 2x baseline latency. No critical resource exhaustion, CPU memory hitting limits, DB pool maxing out. Kafka consumer lag for critical topics must remain manageable, ERG 1 minute.
Okay, that covers load. What about the chaos engineering implementation in more detail? You mentioned Chaos Mesh.
Yes. Chaos Mesh is our primary tool for orchestrating chaos within Kubernetes. We define experiments as custom Kubernetes resources, YAML files stored in Git, of course. Chaos Mesh provides various fault types out of the box, killing pods, injecting network latency or loss between specific pods using Iptable's rules managed by its side cardamom set, stressing CPU or memory, messing with the system clock, etc.
What are some of the most critical chaos scenarios you regularly run?
We focus on scenarios that test our resilience patterns for critical infrastructure dependencies. Database failover. Simulating a primary PostgreSQL RDS instance failing over to a replica during active financial transactions in the account service. We verify that in-flight transactions either complete correctly after failover or are safely rolled back, and no data is lost or corrupted. Carrier API failure. Simulating a complete outage, AG 100% error rate or extreme latency of a major carrier's API like FedEx during label generation requests. We verify that the courier service's circuit breakers strip correctly, traffic is potentially rerouted to other carriers, and user requests don't hang indefinitely. Network partition. Simulating loss of network connectivity between two critical services like the order service and the account service, or between availability zones. We verify the services handle the timeouts gracefully and potentially use fallback mechanisms or queue work for later processing. Clock skew. Intentionally introducing clock differences between pods running the inventory sync service, which uses CRDTs, and other services interacting with it. We verify that the CRDT merge logic, using vector clocks, correctly resolves conflicts despite the skew, preventing data loss. Redis failover. Simulating a Redis master node failure in our Elasticache cluster during operations that rely on Redis for locking or idempotency checks, like payment webhook processing.
We verify that failover to a replica occurs quickly and that operations can continue without data inconsistency.
How do you know if the system responded correctly during these chaos tests? Is it manual verification?
Mostly automated validation. Our monitoring and alerting systems are key here. We define assertions based on expected system behavior during the fault. For example, during the carrier API failure test, we assert that the circuit breaker for that carrier trips, metric increases, error rates for that carrier spike but don't cascade to other carriers, and overall system availability remains within SLOs. If these assertions pass, the chaos experiment is considered successful.
And this is all integrated into the pipeline.
Yes, the reliability testing integration into CI/CD is crucial. Pre-commit. Hooks might run basic unit tests covering failure scenarios. CI pipeline runs automated service-level load tests for critical paths and maybe some non-disruptive chaos experiments like latency injection. Collects baseline reliability metrics. Staging environment. This is where the heavy lifting happens. We run full-scale load tests simulating peak traffic and execute the most critical, potentially disruptive chaos experiments like DV failovers. Automated reliability validation against SLOs determines if the build is fit for production. We run controlled, less disruptive chaos experiments continuously during off-peak hours. Canary deployments rely heavily on comparing reliability metrics, latency errors between the Canary and baseline with automatic rollback triggered by metric degradation.
So reliability is constantly being tested and validated, from code commit all the way to production operation.
That's the goal, building confidence through continuous verification.
Okay, building confidence is key, especially when dealing with money. Let's focus on part 7, financial operations and compliance, the trust factor. How does Shiprocket ensure financial accuracy and meet compliance needs?
This is absolutely non-negotiable. It starts with meticulous financial controls and audit trail.
What does that entail? How do you create an audit trail?
We have a transaction audit trail system. Every single financial transaction, wallet recharge, shipping fee deduction, CID settlement, refund is recorded immutably with its full context. We use dedicated tables in PostgreSQL, often configured with restricted permissions, for example, append-only access enforced via triggers or permissions, to ensure immutability.
What kind of details are captured in this audit log?
Everything needed for a full reconstruction and audit. A high-precision timestamp, down to nanoseconds if possible, the user ID or service account that initiated the action, the full request payload that triggered the financial operation, the full response payload, the source IP address, a unique transaction ID that can be used to correlate logs across multiple services involved in the operation, the before-after balance, etc.
And how is this used for financial audit implementation?
This detailed, immutable log is the foundation. Internal and external auditors can be granted read-only access to query this data. Its richness allows them to trace every penny, verify calculations, confirm approvals, and ensure compliance with financial regulations. We also build internal reports and dashboards directly from this audit data for continuous monitoring.
Okay, audit trails are essential, but what about finding errors before an audit? Reconciliation and discrepancy resolution.
Yes, proactive reconciliation is critical. We have a largely automated reconciliation process that runs frequently, often daily or even hourly, for critical flows.
What are the steps in this automated process?
Typically. 1. Data collection. The reconciliation service gathers financial transaction data from multiple sources. The account service ledger, payment service records, payment gateway settlement reports, carrier COD remittance files, bank statements. 2. Matching. It attempts to automatically match corresponding transactions across these different systems using common identifiers like transaction IDs, order IDs, tracking numbers. 3. Discrepancy identification. Any transactions that cannot be matched or where matched transactions show different amounts or statuses are flagged as discrepancies. 4. Root cause analysis, automated assisted. Simple discrepancies might be automatically categorized, e.g. timing difference versus amount mismatch. Complex ones are flagged for human review. 5. Resolution. Discrepancies are investigated by the financial operations team. Corrections are made through controlled, auditable mechanisms, e.g. manual ledger adjustments requiring approval. 6. Reporting. Dashboards and reports summarize the reconciliation status, highlight outstanding discrepancies, and track resolution times.
So it's a continuous cycle of matching and investigating exceptions.
Exactly. The goal is to catch and fix any issues as quickly as possible, maintaining the integrity of the financial records constantly.
We talked about the dead letter queue, DLQ for the account service, where failed compensating transactions end up. How does the financial operations team handle those? What are their procedures?
The DLQ management process is a formal, documented procedure. 1. Daily review. The FinOps team reviews the contents of the financial DLQs every business day. 2. Triage. Each item is assessed and categorized based on potential impact and urgency. 3. Investigation. The team uses the data in the DLQ message, which includes the original event, error details, trace IDs, and cross-references with the audit trails and logs to understand why the compensating transaction failed. Was it a temporary glitch, a data inconsistency, a bug? 4. Resolution. Based on the investigation, they take the appropriate corrective action. This might involve manually executing the compensating logic, correcting underlying data, or escalating a bug to the engineering team. All manual interventions are logged and require appropriate approvals. 5. Verification. After taking corrective action, they verify that the ledger is now consistent and the issue is truly resolved. 6. Documentation. The resolution steps and outcome are documented for audit purposes and potential process improvement.
So the DLQ acts as a critical human checkpoint for the rare but potentially serious failures that automation couldn't fully resolve.
Precisely. It's the final backstop ensuring financial accuracy, combining automated safeguards with necessary human oversight.
Okay, we've covered the tech in incredible detail. Let's bring it all together in Part 8. Real-world implementation details tailored for the Indian market. How does this architecture directly support Shiprocket's business model and address the specific nuances of operating in India?
That's a great question because the architecture isn't just technically sound, it's deeply integrated with the business strategy and the realities of the target market. Let's look at Shiprocket's business model integration first.
How does the tech enable their core offerings?
Well, the multi-channel integration strategy is directly enabled by the platform sync service we discussed. It allows sellers to easily connect their various online stores, Shopify, WooCommerce, etc., for seamless order syncing and automated workflow management, which is a core part of Shiprocket's appeal.
And the carrier choice.
That's the carrier aggregation model, powered by the courier service and its gateway per carrier architecture. Businesses get access to multiple courier partners through a single platform. The system provides intelligent carrier selection based on speed, cost, and PIN code coverage, leveraging the negotiated rates Shiprocket has secured due to its volume.
What about returns?
The reverse logistics framework is handled by the return management service. It automates the returns process, provides return label generation, and offers tracking for return shipments, a critical component for e-commerce customer satisfaction.
And the analytics.
Analytics and reporting are provided by the Reports and Reconciliation Service, fed by that robust CDC pipeline. It gives sellers insights into their shipping performance, helping them make data-driven decisions to optimize costs and delivery times using customizable reports.
Okay, so the architecture clearly maps to the business features. Now, what about the real-world implementation considerations? Specifics of the Indian market. This seems crucial.
It's incredibly important. India has unique logistics challenges and requirements that the architecture must address. PIN code-based serviceability. India relies heavily on a 6-digit PIN code system for addressing. Our address validation and locality service is highly optimized for this. It doesn't just check if a PIN code is valid. It contains detailed regional knowledge, which delivery office serves it, carrier serviceability nuances for that specific PIN code, state district boundaries, typical transit times, any local restrictions. This level of detail is essential for accurate serviceability checks and delivery estimates across India. GST compliance. India's Goods and Services Tax, GST system, is complex, with varying rates and rules. The dedicated Invoices and GST Management Service ensures that all shipping invoices and financial settlements generated are fully compliant with the latest GST regulations, including correct HSN codes, tax calculations, and invoice formatting. This is a mandatory requirement for businesses operating in India. NDR management. As we discussed, the higher rate of non-delivery reports in India necessitates a specialized approach. The dedicated NDR management service, with its automation engine and integration with RTO prediction, is a direct response to this specific market challenge, helping sellers manage exceptions efficiently.
So the system has India-specific logic baked in. How does it handle the sheer scale of Indian e-commerce?
Scalability for Indian e-commerce was a primary design goal. Festival season handling. The entire architecture, EKS autoscaling, Kafka buffering, database sharding, adaptive circuit breakers, is designed and load tested to handle the massive traffic spikes, often 5x to 10x normal load, experienced during major Indian festival seasons like Diwali, Eid, and others. Regional language support. While the core system operates in English, components like the Platform Sync service and Address Validation service are designed to handle and normalize addresses containing regional language characters, essential for pan-India coverage. Tier 23 city focus. Address validation and carrier serviceability logic are specifically optimized to handle the less structured or more ambiguous addressing patterns often found in smaller Tier 2 and Tier 3 cities in India, ensuring Shiprocket can serve businesses targeting customers beyond the major metros.
It sounds like operational details are also tailored.
Yes, operational excellence features cater to local needs. Pickup scheduling optimization. The pickup scheduling service helps coordinate efficient pickups between sellers and carriers, considering carrier cutoff times and route optimization, which is crucial given traffic and logistical complexities. Manifest generation. The manifest management service ensures accurate and timely generation of shipping manifests required by carriers for pickup, streamlining the first-mile logistics. Real-time tracking. The tracking service aims to provide near real-time end-to-end visibility, consolidating updates from various carriers into a single view, which builds trust with both sellers and end customers.
So tying it all together, how does this translate into tangible business benefits realization for Shiprocket's customers?
Ultimately, the architecture delivers. Reduce shipping costs. Through efficient rate comparison provided by the courier service, leveraging Shiprocket's volume discounts, and potentially suggesting optimized packaging. Increase delivery speed. By monitoring carrier performance, intelligently routing shipments via the best available carrier for a given route, and optimizing pickup scheduling. Improved customer experience, primarily through reliable, real-time tracking information, proactive notifications, the example about delays or NDRs, and a streamlined, easy-to-use returns process. Operational efficiency. By automating previously manual tasks like label generation, tracking updates, and NDR handling, centralizing shipping management, and reducing errors through validation and standardization. Data-driven decision-making, empowering businesses with comprehensive analytics on shipping costs, delivery performance, and carrier effectiveness, allowing them to continuously benchmark and improve their logistics strategies.
It really shows how deep technical architecture directly enables and enhances the core business value proposition. Hashtag, tag, tag, outro, outro.
Wow. Well, what stands out to you after walking us through all of that? We've journeyed through an incredibly complex, definitely resilient, and clearly very thoughtfully engineered system.
Yeah, it's quite something when you lay it all out. I think what stands out is how interconnected everything is, and how every piece, from the smallest database detail to the largest cloud service, was chosen with specific trade-offs in mind to meet those core goals of scale, reliability, and integrity.
It's clear this architecture isn't just theory. It's a living, breathing system tackling massive scale and complex real-world challenges every single day. Every choice, the microservices, the specific consistency models, the gateway patterns, the operational tooling, it all feels like it was made with real purpose, often learning from previous iterations.
Absolutely. Nothing exists in isolation. It's an ecosystem designed to work together and, importantly, designed to be resilient when parts inevitably fail or degrade. And for you, the listener, especially if you're that computer science student, hopefully you now have a foundation that lets you see way beyond the surface of just a shipping platform. You can appreciate the intricate layers of technology, the robust engineering principles like DDD and chaos engineering, and the sheer operational discipline required to make millions of shipments happen seamlessly.
It's the kind of system where you can really see distributed systems concepts applied in a high-stakes real-world scenario. The consistency models, the event-driven patterns, the resilience strategies, they aren't just academic, they're business critical.
It really is inspiring.
So maybe a final thought for you to chew on as you continue your own journey, perhaps as a future architect yourself. Considering all the robustness we've discussed, the redundancies, the multiple layers of testing, the chaos engineering, the detailed run books, what's one area of a system like Shiprocket's, despite all these measures, that you think might still face an unexpected, truly novel challenge in the future? Something maybe unforeseen. And why?
Something for you to mull over, or perhaps explore on your own. Maybe it'll spark an idea for your own projects. Thank you so much for joining us on this deep dive.
Yeah, thanks for listening.
We'll catch you next time.